In this video, we're going to walk through the basics of a simple linear regression model. We're going to prepare a scatter graph. We're going to introduce some of Excel's statistical functions, as well as use the data analysis pack to run a linear regression model. We've been given 24 months of cost data for the 3C Corporation and have been asked to prepare a linear regression model to estimate overhead costs using repair hours. We need to prepare a scatter graph, use Excel's statistical functions, run a simple linear regression, and answer some questions. And we're going to do this twice, once using 12 months of data and once using 24 months of data. You may need to add in Excel statistical analysis data pack to get to the regression tools. There's a link over here on how to do that. So first thing we're going to do is prepare our scatter graph. We're going to select the first 12 months of data, the repair hours and the overhead costs. Highlight it, come up to Insert, Chart, and a scatter graph. Once we have the scatter graph, we can move that scatter graph and size it to fit the provided openings. And I'm also going to ask you to do some formatting on this graph. One of the first things we're going to do, if we right-click on the y-axis, we're going to format the axis. And I want you to set it so the minimum value is 6,000. Next thing we're going to want to do, we can be on the chart, and we're going to come up to Chart Design, add an element, add axes, horizontal, vertical, and then we can also add a chart title. So axes, horizontal, and this was repair hours. Enter. Again, add an element, axes, vertical, overhead cost, enter. On your chart again, add an element, chart title, above chart, estimating overhead cost. And then we're going to need to do some other things. We're going to add a trend line, and we're going to add an estimated linear regression line and include an R-square statistic. To do that, come over to your data. On one of the data points, we're going to right-click, add a trend line. We have linear. We're going to display the equation on the chart, and we're going to display the R-square on the chart. Once we've done that, move that information up to the left, and we can move the chart title over so we can see things a little better. And your charts should basically look like this. We'll repeat this for the 24-month data set as well. One thing you can do is if you copy your chart, paste it down below. We've got a duplicate chart. Right-click on the data, select data, and notice my data went down to row 21 right now. I'm going to choose instead 33. And I have now a 24-month scatter graph. And we can see we have our cost equation for using 12 months of data. It's y equals 4.14, or basically $4.15 increase in repair costs for every hour of repairs, plus our fixed intercept. And we have our R-square, which you recall gives us the explanatory power of our model. So we're explaining roughly 16% of the variability in our overhead cost using repair hours as our independent variable. When we have a larger data set, our estimated equation changes a bit, as might be expected, as does our R-square. We have more data to base our model on, so we would expect better explanatory power. We'll come back and talk more about our coefficients, as well as our R-square and our predictive ability of our model after a while. Let's go ahead and take a look at how we would come up with these same numbers using Excel's functions. But first, let's answer some basic questions. In our regression model, what is our independent variable? Our independent variable is repair hours. We are using that to predict the dependent variable, which is overhead cost. Our hypothesis is that overhead costs depends on repair hours. In our regression equation, what letter represents the independent variable? That would be x. And the dependent variable is represented by the letter y. Now we're going to estimate our intercept, slope, and the r-square by using Excel's functions. We'll begin by estimating the intercept equals intercept, and you can see an Excel function pops up. And we can go up to the top and click on the function wizard to get the pop-up boxes. And again, we're simply going to use the function wizard. So again, once you start typing in a function, it will pop up, and hitting the FX box button will bring up a pop-up box. Our known y's, again, our known y's, what is it we're trying to predict? We are trying to predict our overhead costs. And again, 12 months of data to start with. Our known x's, 12 months worth of data, and hit OK. Our slope equals SOLOPE, parenthesis, and again, we can enter our known y's and x's directly, or invoke the function wizard, our known y's, 12 months of overhead costs, our known x's, 12 months of repair hours, and hit OK. Finally, the r-square equals our SQ, parenthesis, we can enter our known y's or x's or use our pop-up function wizard. Again, overhead costs for y, our known x's, repair hours. And we would do the same for 24 months. One thing we should note is that our estimates for our intercept, our slope, and our r-square are consistent with those we got using a trend line on our scatter graph. One of the advantages of preparing a scatter graph is it will allow us to examine outliers, data points that might not be consistent with the others. This could be due to data input errors or other causes. We'll discuss these later. Let's go ahead now and answer some questions using our regression output. For the 12-month model, how much of the variability in overhead cost can be explained by the variability in repair hours? And that is given by answers given by the r-square. 15.7% of the overall variation in our overhead costs from month to month can be explained by variations in repair hours. Not a lot of explanatory power. Using our 24-month model with data, bigger data set, we're explaining roughly 22% of the overall variability in overhead costs can be explained by variability in repair hours. What likely accounts for the greater explanatory power of our 24-month model? Quite simply, we're making use of more information. We've got more data points to estimate our cost equation. What is the estimated overhead cost in a month with 400 repair hours using our 12-month model? Again, we're simply using our equation, linear equation form, y equals a plus bx. So we've got our intercept of $7,499 plus 400 repair hours times our slope intercept of $4.15 per repair hour. We would estimate costs of $9,158. If we had used the data from our equation from our 24-month model, we would estimate the $7,844 plus $6.90 per repair hour. We would estimate a total cost of $10,603. One thing we should note to be careful of, we want to be sure we are estimating costs within our relevant range. By that, we mean if we look at our independent variable repair hours. We have information for overhead costs for a low of 150 repair hours up to a high of 693 repair hours. We wouldn't want to try to estimate overhead costs if we were using, say, 800 repair hours or 50 repair hours. This is outside of our relevant range. We don't have data that spans those levels of activity. The next thing we're going to want to do is use Excel's data analysis tool pack and run a simple linear regression using all 24 months of data. And I want you to be sure to select labels and print your output to cell C125. Let's go ahead and do that. So we come up top to the Data tab, Data Analysis, Regression. Our input range will be what we're trying to predict, which was our overhead cost. And we're going to include the overhead cost up top because we're going to use data labels. Our independent variable was our repair hours. Check the box that says labels, and we're going to put our data down in cell 125. And here is our regression output. Let's take a look at our regression output. First thing we can pick up is our R squared. And our R squared for our regression output is 21.95, or basically the same 22% that we calculated using our Excel function. So yes, it agrees with our Excel function. What is our intercept? Our intercept is 7,843. And once again, yes, it agrees with the output from our Excel function. And then finally our slope coefficient of $6.90, and it too agrees with what we got with our Excel functions. Our regression output gives us some additional information that's important for us. And the things that we're going to want to pay attention to primarily are our p-values, t-stat, and standard error. So let's go ahead and talk about what those mean. This will take a little bit of a review from our basic statistics. Let's begin by taking a look at our intercept. Again, our coefficient, the same one we estimated earlier, 7,844. Our standard error from a regression output, 1,239. Our t-stat calculated, and our t-stat is simply our coefficient divided by our standard error. Coefficient divided by the standard error is 6.33. Our t-stat from our regression output is also the same, 6.33. And our p-value from our regression output is basically 0. Let's go ahead and pick the same numbers up for our repair hours, and then we'll talk about what these things mean. Our slope coefficient, 6.9, and again, that's the coefficient for our x variable in our regression equation. Our standard error, 2.77. Our calculated t-stat is simply taking our slope coefficient divided by the standard error, and we get 2.49, which is in agreement with the t-stat displayed in our regression output. And then finally, a p-value of 0.02 or 2.1%. Let's go ahead and talk about what these variables mean and what this information tells us. The slope coefficient for repair hours represents our best estimate of the change in total overhead costs for an additional hour of repairs. The 690 is not the actual amount that overhead cost will change, which is unknown, just our best estimate given our 24 months of data. Recall, using 12 months of data, we had a different estimate, $4.15, and using 25 months, it would be different again. Presumably, the more data we use, the better or more reliable our estimate. When we run a regression model, our null hypothesis is that the slope coefficient is 0. That is, that there's no relationship between the dependent variable, cost, and our independent variable, repair hours in this case. That is, working more or less repair hours will not change our total overhead cost. Our t-stat, or p-value, will help us interpret our regression results. And our t-stat, again, it's calculated by simply dividing the estimated coefficient by our standard error. Let's take a look and see what it means. The null hypothesis is that the slope coefficient is 0. That is, no relationship between repair hours and overhead costs. And in our equation, y equals a plus bx, that means b would be 0. With our 24, which is shown right over here on our graph, with our 24 months of data, our best estimate is $6.90. That is, every additional repair hour leads to a $6.90 increase in total overhead cost. And we need to ask, is this a good estimate? Is the null hypothesis that b equals 0 true? To answer this question, we need to look at our standard normal distribution, which tells us how far a sample mean is likely to lie from our true underlying population mean. Recall that if our data is normally distributed, that means there's a 68% chance that our sample mean will fall within plus or minus 1 standard deviation of 0. If our and there's a 95% chance that our population, or sample mean rather, will fall within 95% chance that it will fall within 2 standard deviations of our hypothesized mean of 0. Based on our 24-month sample, our estimate for the slope is b equals 6.90, and that's 2.4 standard errors away from the null hypothesis mean of b equaling 0. And it's way out here on the right-hand side of our distribution. Our p-value of 2.1% tells us that there's only a very small chance that repair hours and overhead costs are unrelated. That is, that the true value for b is 0. In fact, there's only a 2.1% chance that b equals 0, given our best estimate based on our 24 months of data, which was $6.90 per hour of repair hours, in cost per hour of repair hours. So for us to get an estimate of 6.9 for the slope coefficient, when the true coefficient is 0, is very unlikely. There's only about a 2% chance that this would happen if the true value was 0. Again, we're not saying the true value is $6.90. We're just saying that there's a pretty strong chance that it's not 0, that it's something other than 0. We're, from our data, say that there's only a 2.1% chance that the true value of b is equal to 0. For the fixed intercept, our estimated cost is $7,844 compared to, again, a null hypothesis that the intercept A would equal 0. We came up with 7,844, and that's 6.33 standard errors away from the null hypothesis of A equals 0. This is way, 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 way out in the far right-hand tail of the distribution. In fact, our p-value tells us the probability associated with this particular standard error is essentially 0. From our regression output in scientific notation, it's 2.26 to the 0.0 with 6 leading zeros. Again, essentially 0. Again, this doesn't mean the true value for fixed cost is $7,844. With a different sample, we would have a different estimate, but we can feel extremely confident that it's certainly not 0. So again, our R-square tells us how much of the variation in our dependent variable, overhead cost, has been explained by repair hours. In this case, we can explain roughly 22% of the variability in cost by variability in the underlying repair hours. We can then use our regression output to estimate our cost equation. The intercept gives us our fixed cost, our y-intercept, and the slope coefficient of $6.90 is our best estimate of the variability in our cost based on changes in repair hours. We can get some sort of degree of confidence regarding the strength of the relationship or our level of confidence that both of these variables are not really zero, which is our null hypothesis, by looking at our t-stat or p-value, and both of them essentially tell us the same thing. A t-stat of 6.33 tells us that this is 6.3 standard deviations away from zero. A t-stat of 2.48 tells us that our estimate of 6.89 for our slope coefficient is 2.48 standard deviations away from zero, and the associated probabilities of that happening are 2% and basically 0. If we want to look at the overall viability or significance of our total model, not only do we look at our R-square, which tells us how much of our variability we've explained, but we can look at the f-statistics and the related p-value or significant level of that. These can also be interpreted much as we would our t-stat and p-value for our coefficient and for our slope. We'll take a look at these a little bit further when we examine a multiple linear regression model.